Well, good morning. This is something like 11:02 on Thursday, the whatever day it is, in 17th of November, 2016. Supposed to be linear algebra class, Math 237. However, I'm the only one in the room, so hopefully someone will be coming in. However, in the 238 class, just before that, nobody was here for that one either, so I'm just recording by myself, which is pretty boring, but we can do it, okay? Did want to remind you of a couple things. Because next week is Thanksgiving week, and you lucky people have the whole week off. We will be here Monday, Tuesday, and Wednesday. Now, some people will be down in Montgomery at professional meetings there Monday and Tuesday. The rest of us will be here on campus if we don't take personal leave or something, which I'm not planning to, but some may be. So you have the whole week off. We don't. And by the way, the college will be open Monday, Tuesday, and Wednesday. Everything's closed Thursday and Friday. That's state holidays. Monday, Tuesday, Wednesday, the college is open. We may be short-staffed because a lot of people will be in Montgomery, but we will be open. However, if you're looking for instructors, instructors will be occupied, generally they do anyway, Monday and Tuesday in local professional development, and usually that's over on the Birmingham campus. I haven't seen where it is this time, but just, check and see. And if we are over there, we're probably not very available because they'll have us in a meeting room somewhere, usually the ACAT Theater on the first floor. So we'll be down there. So you won't be able to get us easily Monday or Tuesday. Wednesday, we should be back in our offices again if people don't take personal leave. So if you have business to do with the college, all the offices will be open Monday and Tuesday and at least Wednesday morning. Now, the reason I say that, usually by Wednesday afternoon, sometime in the afternoon, maybe right at noon, maybe 2, maybe 4, sometime or another in the afternoon, they usually, not always, they aren't required to, but let people go early. So if you have business to do with the college, get it done Monday, Tuesday, or Wednesday morning. I wouldn't wait till Wednesday afternoon. You may not find the person you need, or anyone maybe, to help you. So if you're trying to find instructors, those in Montgomery are out of pocket completely. Those who are not in Montgomery will probably be in professional development Monday and Tuesday. But Wednesday, somebody will be back in their offices, okay? I plan to be in mine, but I don't know how long till they let us go, or unless we have company come into town or something that I have to take personal leave as well. So anyway, that's coming up. But the other thing I wanted to mention is I've only received papers from one of you 3 students. The other 2, please be working on your papers so you can get those in. Secondly, all 3 people have turned in the first test. I just got the last one graded last night. I haven't got it on Blackboard yet, but it will be there. So I was going to return those papers to you today for any who were here. However, nobody's here, so I can't do that. Now, second test, 2 out of the 3 people have turned in. Still waiting for the third one on that. And the third test will be coming up fairly soon, okay? Not before Thanksgiving, obviously. Okay. I don't know how much more we'll get done before the end of the term, but we'll get it done as much as we can. So please get these things in, especially your research paper, and as much as possible you can on the other. I just realized I have the wrong book open. Let me... Sorry, I still had the differential equations book open. I was thinking, where are we here? All right, we're in, I believe we're on page, I think, 196, chapter 4, vector spaces, 4.6, rank of a matrix and systems of linear equations. I wish there were someone here to see if there were any questions. There's nobody here. So let's proceed from this. All right. Now, there's part of me that thinks we've already hit some of this, but I can't say that for absolute certain, so let's do it now. There are 417, top of page 196, section 4.6. If A is an M by N matrix, okay, of rank R, okay. Now, just wanting to remind you of what the rank was, okay? Back on page 193, definition of rank. The dimension of the row or column space of a matrix is called the rank of the matrix. The dimension of the row or column space of a matrix is called the rank of a matrix. Now, how do you find that? Whatever matrix you have, do row reduction. Okay? And then, generally, you get it to row echelon form. Okay? And then count the number of non-zero leading elements in each row, and that's going to be the rank of the matrix. Okay? Example 6 on that same page, do row reduction, you have 3 leading ones, rank 3. Example 7 on page 195, do row reduction, you have 2 leading ones. There, that's rank 2. Okay? Yeah, we'll be doing others. So that's what the rank is. So we have an M by N matrix of rank R. That means when you do the row reduction, get it into row echelon form, you have you have R, and here's another way to express that. You have R non-zero rows. Okay, that's the rank of the matrix. Okay, now, so that's the R. If you have this, then the dimension of the solution space now they have actually, I don't recall, of the solution space of this matrix equation, AX is equal to 0, or is it B? Yeah, 0. Is the rank, the dimension of that solution space is N minus R. Okay, what's N? N is a number of columns. Okay, so the dimension of the solution space is N minus R. Okay, so let's step back for just a moment and see what we got here. Here we have M rows in a matrix. You do your row reduction. How many rows of those M rows wind up with, sorry, I can hardly talk, wind up with non-zero rows? How many of those are non-zero rows? Well, that's going to be your rank. Okay? So, that means you have M rows, R of those are non-zero, so that means M minus R is the number of 0 rows that you have, all 0 rows. Okay? Now, let's go to the columns. The dimension of your solution space is your N minus R. Okay? Because you have R is how many leading ones you have, basically. How many rows have leading ones, or leading non-zero entries. And that's going to be your R. So the number of columns that don't have those leading ones, that's going to be the dimension of your solution space. Okay? And remember, what do we mean by that? those were the columns that you assigned your arbitrary parameters to. So therefore, you are going to, the dimension is going to be how big a space is that, okay? N minus R. Okay. Now, one more topic or sentence on here, that is N is equal to the rank R, rank of A, R, plus the nullity. Nullity, I'm sorry, I keep saying nullity, but nullity, okay? Well, what does that mean? The nullity is the dimension of the null space. What is the null space? This is on page 194. If A is an M by N matrix, then the set of all solutions of the homogeneous system of the linear equation AX equal N is a subspace of R called the null space of A and is denoted by N of A. Okay? The dimension of that null space is the nullity. I guess is how you pronounce that word. The null space of A is also called the solution space of the matrix AX equals 0. Okay? So, here is another way, and I wish the book had approached it this way. To me, that makes the most sense. Okay? But that's just me. If you go back to example 6 on page 193, notice that's an 3 by 4 matrix. Okay? There are 3 leading ones when you do the row reduction. That means the rank of this matrix is 3. There are no 0 rows. I wish they'd have said it this way. That's the nullity. 0 is the nullity of that one. Okay, now they didn't say it because we hadn't had the definition yet. Okay, so let's look at example 7. Another 3 by 4. But when you do a row reduction on that one, you get 2 leading ones, 2 rows with leading ones, so its rank is 2. I'm trying to see where they say that. I don't see that they do say it. But let's us say that the rank is 2. The number of all 0 rows is 1, so the nullity is 1. Okay? So now we have that the rank plus the nullity, I'm sorry, said it wrong. Yacht is the number of columns, not rows. Okay. Go back to that one. The rank is 2. The number of columns is 4, so the nullity is 2. Okay? Now, where do you get the nullity of 2? Basically, the other way to look at this, and I was saying number of 0 rows, that's not the nullity. Sorry about that. It's the number of, I want to make sure I say it right. The dimension of the solution space is N minus R. I'm sorry. The rank of the rank, I'm sorry, is the number of these terms are so similar. The dimension of the row or column space of matrix A is the rank of the matrix, and that's how many, when you do row reduction, how many leading ones you have in your rows. Okay, that's the rank. Okay, now the rank minus, okay, in the number of rows minus the rank is the nullity. Okay, so going back to page 193, example 6, that's a 3 by 4 matrix. There are 4 columns. The rank is 3, so the nullity is 1. Nullity is 1. I guess is how you say that. Okay? Now, the dimension of the solution space is the number of columns minus the rank. On that one, the dimension of the solution space was 1. Okay? Let's go to example 7. It's a 3 by 4 matrix again, but when you do your row reduction, you only have 2 leading ones, 2 rows with leading ones, so its rank is 2. Its nullity is the number of columns minus the rank, which is, the solution space, the dimension of the solution space is number of columns minus the rank, which is 2, and the nullity is in dimension of the, the dimension of the solution space is n minus 2, and the nullity is n minus r, and the nullity is also n minus r. So it basically is saying the dimension of the solution space of that, but yeah, that is the nullity. So the nullity and dimension of the solution space of the homogeneous solution is indeed the same. That's the same word. Sorry about that. I was getting crossed up rows and columns. They are the same. So sorry, I really messed that one up. Let's do example 8. Let's show this. Let the column vectors of the matrix A be denoted by, and let me clear all this off. And, before we do that, the dimension of the solution space is n minus r, so dimension of the solution space is also called the nullity. And what is it? Solution of this, and if I hadn't had my blinders on here, that's exactly what it is. Dimension of the null space. What is the null space of A? It's the set of all solutions of the homogeneous system. That's the null space. The dimension of that is the nullity, and the nullity is the same as the dimensions. Yeah, it's just going in circles there. Sorry. That's what got me confused. It's saying the same thing as the previous, except it's giving it a different name. I'm sorry. So, anyway, let's go to example 8. So let me clear this out of the way. Okay. Let the column vectors of this matrix A, and I'll write it down, A is equal to 1, 0, negative 2, 0. Okay. I'm writing them that way because they're saying they're column vectors. Okay, that's the only reason I am, not because someone's influenced me. Okay, 0, negative 1, 3, 0, negative 1, negative 1, 3. Negative 2, negative 3, 1, 9. Negative 2, negative 3, 1, 9. 1, 1, negative 1, 0. And 0, 3, 3, negative 12. Okay. Now, what they're saying is let the column vectors of that matrix be denoted by A1, A2, A3, A4, and A5. Okay, done. Find the rank and nullity of A. What is the rank of A? Well, to get the rank, we do our row reductions. Okay, so 2 times row 1 plus row 3, that's going to wipe out that one. So this produces, I'm going to try to squash it up a little bit, 1, 0, negative 2, 1, 0. That was easy to squash. 0, negative 1, negative 3, 1, 3. If I wrote that right, yes I did. And then this would be a 0, because 2 times 1 is 2, minus 2 is 0. This will be a negative 1. This will be a negative 4 plus 1 is negative 3. That will be a 2 minus 1 is 1. And that will be a 3. Okay? And then we write down the last one. 0, 3, 9, 0, minus 12. Okay. Now, I hope it's pretty obvious. The second and third rows are the same. So then we could basically make this one all zeros. And technically, take it to the bottom. Okay? Now, we'll also change signs of this one. Oops. Okay. And that will be your new row 2. Then we will do, should have done this first, minus 3 row 2 plus row 4. It's now going to be our new row 3, by the way, when we move it up. This will produce this one. 1, 0, minus 2, 1, 0. 0, 1, 3, minus 1, minus 3. I'm going to make my bottom row the all 0 row. And the fourth row becomes the third row. This will be a 0. That will be a 0. Because minus 3 times 1 is minus 3 plus 3 is 0. Minus 3 times 3 is minus 9 plus 9 is 0. And minus 3 times minus 1 is 3. So that becomes a 3. And then that stays a 3. All right. Now, it's pretty easy to make those ones. You don't have to, but I'm doing. All right. Let's see if now we can answer the questions. Find the rank of A. The rank of A is equal to 3. 3 leading ones. And let me see, I forget what this symbol for rank. No, they write out the word rank. I just put R of A. I was thinking I needed to do a little r of A. I think I prefer little r. Or most correct is write out the word rank. Rank of that vector is A because you have 3 leading ones or leading non-zeros. All right. Now, the nullity of A, and do they have a symbol for that? It seems like they don't. I wish they did. The null space of A is capital N of A. I want to call the nullity little n of A. Now that's probably not good. They'll probably name something else there later. But this is nullity. Okay, I won't spell it all out, but that's nullity, okay, of A. What would that be? Goodness gracious. From what we just had, the number of columns, 5, minus the rank is 2. And that's also the rank of our solution space for the homogeneous equation. In other words, you'll have a parameter for the 5th column and a parameter for the 3rd column. So that nullity is 2, or the dimension of the solution space of that. Okay, they did their row reductions, and the only problem is my matrix doesn't look like theirs. I must have made an error somewhere. The 1, 0, negative 2, oh, I see why it doesn't. Because they did a reduced row echelon form. So let's go on and do reduced row echelon form. This is fine, that's fine. We just got 2 things to correct here. So that'll be minus row 3 plus row 1. And we'll do a row 3 plus row 1. No, row 2, sorry. Okay, so do that one more thing here, just to get it to look like theirs. So we're using row 3, which is 0, 0, 0, 1, 1. But that's the thing I really wanted to check. Let me make sure that I haven't made an error with that one. Goodness, my stomach is growling like crazy. So, minus 3 row, okay, make sure I have that right. Looks like I got it right, but let's see. Minus 3 row 2 plus row 4. Okay, that would be minus 3 plus 3 is 0. Good. Minus 9 plus 9 is 0. Good. 3 plus 0 is 3, right? And 9 minus 12 is minus 3. So sure enough, that is a minus 1. Sorry, I'm going too fast. Positive 9 minus 12 is minus 3. That became a minus 1, so that's a minus 1. I wanted to do that before I did these 2 row reductions, so it would have been wrong. Okay, so doing the first one, minus row 3 plus row 1, that would be a 1. That would be a 0. That would be a minus 2. That would be a 0. And that would be a, if I can read it, 1. Okay? Then adding row 3 and row 2, that would be a 0, a 1, a 3, a 0, and a minus 4. Yes, now we got the same thing. And our last row still is all zeros. Okay, they just reduced row echelon form. I just done row echelon form, which gives you all the information, but they just took it one more step. So, because B has 3 non-zero rows, the rank of A is 3. And that's what I said before. They never quite phrased it that way before, but that's the best way to look at it, the number of non-zero rows. Okay? All right. Now, the second thing is the nullity. And the nullity is the number of columns minus the rank, and that gives you 2. So we got that. We got both of those right. Okay. The B part says, find a subset of the column vectors of A that forms a basis for the column space of A. Find a subset of the column vectors of A that forms a basis for the column space of A. Okay? Now, a subset of the column vectors of A that forms a basis. Okay. So since your three columns that have the leading ones in them, the leading ones are then the rows, but the three columns that contain those are the ones that resulted from A1, A2, and A4. That means A1, A2, and A4 should be that subset of the column vectors of A that form a basis for the column space of A. Now, they were A1, 1's 0, -2, 0, A2, which is 0, -1, -1, 3, and A4, which was 1, 1, 1, 1, 1, -1, 0. Yes, exactly. Okay. I didn't write them down, but these would be the three columns that form the basis for your column space of A. And the dimension of the column space is 3, so it has to have 3 vectors, because that's the rank. Okay. Rank of column space, rank of row space are the same. They just call it the rank. All right, let's move on to solutions of systems of linear equations. You now know that the set of all solution vectors of the homogeneous linear system AX, had it written down before, AX equals 0 is a subspace. The set of all solution vectors of that homogeneous linear system is a subspace. The set of all solution vectors of the non-homogeneous system, AX equal B, where B is not the 0 vector, is not a subspace because the 0 vector is never a solution of a non-homogeneous system. There is a relationship, however, between the sets of solutions of the two systems, AX equals 0 and AX equal B, specifically if X sub P, okay, is a particular solution of the non-homogeneous solution system, AX equal B, then every solution of that system can be written as X is equal to X sub P, which is that particular solution, plus X sub H, where X sub H is a solution of the corresponding homogeneous system. Okay? And every solution of that system can be written as X sub H plus X sub P, where the X sub P is a particular solution of the non-homogeneous system, and X sub H is any of the solutions of your homogeneous system. Okay? So that's what the next theorem states, and I'll write that one down. If X sub P, vector X sub P, is a particular solution for those people in differential equations, this is same terminology here. Particular solution of the non-homogeneous system AX equal B, not a very pretty equal sign. My screen keeps bouncing on me. Okay? Then, if that's the case, then the conclusion is every solution of this system can be written okay, in the form x is your solution is equal to x sub p, that particular solution, plus x sub h, which is one of the homogeneous solutions to, this is the solution to ax equals 0. Okay. And the proof of this one is ridiculously simple. Okay? Now, remember that ax equals 0, its solutions are called x sub h. Right there. Okay? ax equal p, I'm sorry, I know what I'm trying to say and I can't get the thing to come up here. Okay. Jumping ahead of myself. Ax equal b, where b is not the 0 vector. Okay. And x is a solution for that one. Okay. X of h is a solution for that one. Okay. Now, if that's the case, then, okay, I'm sorry, x sub p. I'm sorry, I left off the p there. X to p is, goodness gracious, I'm sorry, okay. Sorry about this. They're not putting the p in there yet. I knew there was a reason I didn't, but later we're going to call it that. Okay. Let x be a solution to this. That's what we're going to assume. Okay? Now, then, we already know that x sub p is a particular solution for this too. So x sub p is also a solution for this. Okay? Well then, if that's the case, then x minus x sub p, if you put that in front, this would be a solution to the homogeneous case. Okay? Because both of those are solutions for the particular case, so x equal x of p, or x minus x of p, be a solution for the homogeneous case. And because that's true, this is ax minus axp equals 0. You know that ax, this is equal to b, and this is equal to 0, so axp must also equal b for that to be true. Okay? And if that's the case, then x sub h is one of those solutions, so x sub h is equal to x minus x sub p. So then add x sub p to both sides, and you have your general solution, x, I've been leaving off my vector symbols, is equal to x sub h plus x sub p. All right. It just ran around in circles. All right. Let's do example 9. Tired of those. Let's do example 9. Here's a set of equations. x1 minus 2x3 plus x4 is equal to 5. 3x1 plus x2 minus 5x3 is equal to 8. X1 plus 2x2 minus x4 is equal to minus 9. Find the set of all solution vectors of this system of linear equations. All right. So, find the set of all solution vectors for this system of linear equations. Well, what we're going to do is set up our augmented matrix. Okay? The augmented matrix will be 1, 0, negative 2, 1, 5. 3, 1, negative 5, 0, 8. 1, 2, 0, negative 1, negative 9. Okay, we're going to proceed to row reduce this. Sorry. About this point, it starts clogging up. I don't know why. I made it through the first class, no sweat. Second class, no sweat. This class almost always starts clogging up somewhere about midway through the class. And we're pretty close to right there. Okay? So what we're going to do is minus row 1, plus, minus 3 row 1 plus row 2. That will go there, and minus row 1 plus row 3 goes here. Okay, so row 1 stays the same, 1, 0, negative 2, 1, 5, 0, 1, 1, negative 3, negative 7, I believe that's right. Brr, I'm cold. Okay, and the bottom one would be a 0, 2, 2, minus 2, minus 14, believe. Okay? Brr, I'm so sorry. Now, just to make life a little easier, let's divide the third row by 2. Okay? No. 7. All right. Negative 7. Wow. Okay. Now, almost shivering it, so it's just miserable in here. Okay, minus row 2 plus row 3. It's going to be our next step. Okay, row 1 stays the same, 1, 0, minus 2, 1, 5. Row 2 stays the same, 0, 1, 1, minus 3, minus 7. And new row 3 is 0, 0, 0, 1, no, 2. This writing over is not a good idea. 2, and then I think that's a negative. No, I think that's a 0. Interesting. Then we can divide the bottom row by 1. Okay, do we need to do reduce row echelon form? Just be 2 more steps if we did it. Let's see what they do. Okay. I must have botched up something here. Well, it would help if I wrote down the equation right. sorry about that. That's a minus 5 here. So a minus 5 here. And with that in mind, minus row 1 plus row 3 would be let's redo that again. Minus 1 minus 5 is a minus 6. And then I'm dividing by 2, and that makes it a minus 3. Right. Now we see those two rows are the same, so this is a 0 down here. All right. Now, we are in reduced row echelon form already. So the whole purpose of doing this was to get a solution for that system of equations. Okay? Now, they have a bizarre way of doing it, but it certainly is true. I mean, it's okay. What we would have done in the previously, and I'm going to use the same things, let this be S and this be T. Okay? All right. Goodness gracious, I'm cold. We would have said that from this line, either one of them, it doesn't matter. These are the parametric ones. So this says x1 is equal to 5 minus 2s minus plus 2s minus t. Okay, because those things are equal to 5, and then subtracting, which is, and x2 is equal to just because I like to do it this way, 3t minus s minus 7. You don't have to do it that way, but that's how I chose to. Okay, and x3 is equal to s, and x4 is equal to t. All right. Man, it's so cold in here. Okay. So, if you wanted to write this as a vector, just like we got it standing here, that would be x equal to, and that's that column vector here, it would equal to this. It would be it does the S and T first. I don't know why especially, but it doesn't really matter. You could put the S here, and that would be 2 minus 1, 1, 0 plus T times minus 1, 3, 0, 1 plus the vector 5, negative 7, 0, 0. Okay. Now, x of p is a particular solution vector of this thing. Sorry. xp is a particular solution, and by the way, this is xp. There's your xp. The 5, negative 7, 0, 0. Okay. Now, did it matter? We know that's going to work. Okay, I'll just put it that way. Because any value s you put in for s, and any value t you put in for t, just doing all the terms here, that's guaranteed to give you a solution. Okay? And so therefore, the x sub h, which is your homogeneous vector, would then be this part. Okay? They're calling I was trying to find, they don't ever say specifically what U1 and U2 is, but this is U1. I was going to write it down, and I realized they hadn't even said it, and this is U2, which, by the way, is a basis for your solution vectors of the homogeneous form. Okay. And this is what your x of h is then any s times u1 plus t times u2. Okay, where those are those two vectors. They represent the auxiliary or the arbitrary vector in the solution space of that. Any value you put there is going to be solve the equation, the homogeneous equation, where all three of those constants are 0. And this one particular vector is one vector that satisfies the other. Okay? Now, let's just back up just a moment here. Your A, which is your coefficient matrix, which was a 3 by 4, by the way, it had a rank of 2. It had a null space of 2, or nullity of 2, because the number of rows minus rank, that would be 2. And basically, this is basically, you can think of as your null space. That's the solution. So it certainly has a dimension of 2. So its nullity is 2. And what else? I think that's about all. Okay. Now, the next theorem, which I guess I'll go to a clean page here. All right, man, I'm cold. I was going to say something else, but they don't say it in the book, so rather than confuse the issue, let's just go with it. Okay, let's go to clean page. The next theorem describes how the column space of a matrix can be used to determine whether a system of linear equations is consistent. Okay, this is theorem 419. The system, well, my cord is dragging me on, AX equal B. Okay, there's a system of equations. Is consistent, okay, if and only if, this goes both ways here, B is in the column space of A. The B vector, let me do that, is an element of the column space of A. Okay. Whew. All right. For this system, AX equal B that we have here, let A, X, and B be A be the n by sorry, n by m coefficient matrix. And n by 1, the X is an n by 1 column matrix of the unknowns, and B is the m by 1 right hand side that fit there. Okay. Sorry, my head's clogging up. Okay. Now, that's true if and only if that solution vector, column vector B, is the right hand side. Okay. Having trouble breathing. Then this AX, you could spell that out, and A is, I hope you got it, but I hate having to write all this out, but I guess I should. The AX, that part, the left-hand side, A is some vector, some matrix, A11, A12, A13, to A1N, n columns. A21, A22, A23, to A2N. A31, A32, A33, to A3N. A sub M1, A sub M2, A sub M3, A sub M N. All right. Goodness gracious, it's chilly in here. This is multiplied by x sub 1, x sub 2, x sub 3, down to x sub n. Has to be x sub n because to do a m by n multiplication by a column vector, that has to be an m by 1 column vector. Okay? Now, if you were to do that, gory step at gory step, okay? Okay. Let's just picture the A11 x1 plus A22 x12 x2 plus A13 x3 plus A14, all the way down. Okay. Then the next would be A21X1 plus A22X, all the way down, and so forth. Okay? Well, you notice the first column here is multiplied by that column here. So that would be A11, A21, A231, dot, 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 down to AM1 times X1. Okay? Plus, and then you do the same for each one of them. A12, A22, A32, dot, 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 AM2. Okay? And that would be times X2. And you just go on down the line till you get to X of N. Okay? I'll do that one. Plus, dot, 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 down to A sub 1N, A sub 2N, dot, 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 A sub HN times X sub N. Brr. Now they wrote the variable part in front. I like the number part in front. Doesn't matter. Okay. Now for that to equal B, this thing here, left hand side, is equal to B, where B is B1, B2, B3, dot, 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 down to B sub N. Okay. No. B sub M. Okay. Because there were M rows, so they have to be M constants at the end. Equal B sub M. And I wrote it as a column vector. They wrote it as a row vector transposed. Then that's a linear combination of the columns of A. Okay? Where now your X1, X2, X3 actually is, I can't read my writing here. That's an MN. Okay. Yeah. Yeah. That's a linear combination of these column vectors with our coefficients being the X component, the components of X, whatever they happen to be. Okay? The system is consistent if and only if B is in the subspace of Rm spanned by the columns of A. Okay? So they wind up concluding without much more than that is the case, what you're trying to prove. So let's see, can we do example 10 before the end? I think we can. It looks fairly short. Let's see if we can. Consider this system of linear equations. X1 plus X2 minus X3 is equal to -1. Second, X1 plus X3 is equal to 3. Third, 3X1 minus or plus 2X2 minus X3 is equal to 1. Goodness, I hope I got those right this time. Oh, man. Okay. Okay. Where do we go? How do we go? Let's just do our augmented matrix. 1, 1, -1, -1. 1, 0, 1, 3. 3, 2, minus 1, 1. All right. Goodness gracious. So uncomfortable in here. Minus row 1 plus row 2. Be a 1, 1, minus 1, minus 1. 0, minus 1, 2, 4. Minus 3, row 1 plus row 3. That would be a 0, minus 1. Brr. 3 minus 1 is 2. And 4. Not particularly fantastic, but it's fine. Pretty easy to see this row can become zeros. All right? And if you wanted to, and they do it, make this minus plus plus. I mean plus minus minus. Okay. Negate each of those. Okay. Now they do one more step, and they do reduce row echelon form, which would be, I wish I hadn't done what I did before, but I will. Minus row 2 plus row 1 is the new row 1. So this is going to be 1, 0, 1, 3. This becomes 0, 1, negative 2, negative 4. And these are all zeros. All right. Goodness gracious. And that's the one they turn out with. Now, what does that mean to us? Consider this system. The rank of the coefficient matrix is 2. That's equal to the rank of the augmented matrix. That's 2. Okay. The null space of the coefficient matrix would then be number of columns minus, or nullity, number of columns minus 2. That would be 1. Okay. So the system of linear equations is consistent. Okay. They never ask for it. They just says consider it, and at the end it's consistent. Why is it consistent? Because your bottom row, even though it's all, because it is all zeros, that makes it consistent. If that had been 0, 0, 0, 17, or negative 4/3, or pi halves, or anything other than 0, the fourth entry there, then this would have been an inconsistent system. If those have been ones down your diagonal with, then that would have been consistent, okay? But with a 0 in that last one, you've got it, in the 3 variable places, you have to have a 0 in the constant place, otherwise it's inconsistent. All right, the following summary presents several major results involving systems of linear equations, matrices, determinants, and vector spaces. These are those equivalent conditions we've had before. We're going to have them again. So here they go. Okay? If A is an n by n matrix, okay, then the following conditions are equivalent. Okay? The first, if A is invertible, that implies every one of the rest of these. Number 2, AX equal B has a unique solution for any n by 1 matrix B. Okay? If A is invertible, that guarantees that's going to be the case. Now remember, A is n by n, not n by m, but n by n. If A is invertible, that means we can write it in reduced row echelon form as the identity matrix. That means for sure you get a unique solution for each B that you plug in. Okay? Number 3. And each B you plug in the other also. AX equals 0 must have only the trivial solution. If there were any other solution to it, then A wouldn't have been invertible, okay? And AX plus B wouldn't have been unique. All right? Number 4, A is row equivalent to the identity matrix. A row equivalent to IN. Because A was n by n, A would be. In other words, that means it's invertible. I mean, same thing. 5. The determinant of A is not equal to 0. Because if the determinant of A was equal to 0, that meant it was not invertible. Okay, so the determinant must not equal 0. Okay, number 6. The rank of A is equal to n. In other words, how many non-zero rows that start with a non-zero entry are there? Those are all ones down the diagonal, so there's n of them. Okay? Number 7. That's a new one that we just added. The n rows are linearly independent. N row vectors linearly independent. Another sort of new one. And 8 is the n column vectors linearly independent. Okay? Good deal. All right. Homework exercises. And remember, you can see calcchat.com for worked out solutions with odd number of exercises. They also have odd number of answers in the back. So do these, either 1 or 3 or both. Any of the odds 5 through 9. Either 11 or 13 or both. Either 15 or 17 or both. Any of the odds 19 to 23. Any of the odds 25 through 35. Any of the odds 37 to 45. 45 may take a little extra effort, but definitely try any of the odds 37 to 43. See if you can do 45. Any of the odds 40, do 47. Okay, there's a whole passel of things it's asking for, so do 47. Make sure you understand that. Any of the odds 49 to 53. 53 is a little too hard. Be sure you do at least 49 or 51 or both. Either 55 or 57 or both. And then on the others, you can choose any of the ones you choose to do out of any of the odds 59 through 67. Some of those are proofs, and some of them are other manipulations you need to do. Good idea to look at the true-false questions 69 and 71. And then you could also do a couple of others if you like, 73 and or 75. Okay, we've got about 50 seconds. I think that's a good place to stop, and we'll pick up there next time. So